Let's go, friend. We will be start the next chapter. New chapter is for dynamics of rigid body. Dynamics of rigid body. Okay. Dynamics of rigid body. Introduction. In the inability of a body to change by itself its state of rest or of uniform motion along a straight line, Newton's first law of motion, is an inherent property of every body and is known as inertia. Okay, the greater the mass, larger is its inertia. Therefore, mass is taken as the measure of inertia for linear motion. In the similar manner, a body free to rotate about its axis opposes any change in its rotates of in a state of rest or uniform rotation. In other words, it possesses inertia for rotational motion. That is, the body opposes the torque or moment of the couple of light to it. Hence the name moment of inertia mi of any rigid body depends upon the distribution of its constituent particles about its axis of rotation. Thus, mass in linear motion is analogous to its momentum of inertia in rotational motion. Okay. Okay, that means the distribution of its constitution participates about its axis of rotation. Thus, mass in linear motion, mass is linear motion is analogous to its moment of inertia in rotational motion. Inertia. First heading of this chapter is inertia. First heading of this chapter is inertia. What is inertia? We will be known about inertia. Okay. Inertia. According to Newton's first law of motion, a body at rest will remain at rest, and a body moving with uniform velocity in a straight line will continue to do so unless an external force is applied to it. This property of a body, by virtue of which it is unstable to change its state of rest or of uniform motion in a straight line by itself, is known as inertia. For translatory motion, the value of inertia depends only on the mass of the body. The greater is the mass, greater is the inertia. Okay. According to Newton's first law, according to Newton's first law of motion, a body at rest will be remain. A body at rest will remain at rest, and a body moving with uniform velocity, and a body moving with uniform velocity in a straight line, uniform velocity in a straight line will continue to do so unless an external an external force is applied to it. external force is applied, force is applied to it, force is applied to it, okay? This property of a body by virtue, this property of a body, this property of a body by virtue of a body, by virtue of a body, by virtue of which it is unable, by virtue of which it is unable to change its states, to change its state of rest, or of uniform motion in a straight line, uniform motion in a straight line, by itself is known as, inertia. For translatory motion, the value of inertia depends only on the mass of the body, okay? For translatory motion, the value of inertia, only depends only on the mass of the body, okay? The greater is the mass, greater is the inertia. According to Newton's first law of motion, a body at rest will remain at rest, and a body moving with uniform velocity in a straight line will continue to do so unless an external force is applied to it, okay? This property of a body by virtue of which it is unable to change its state of rest or of uniform motion in a straight line by itself is known as inertia. For translatory motion, the value of inertia depends only on the mass of the body. The greater is the mass, greater is the inertia, okay? Next heading is a moment of inertia. Moment of inertia. Next heading is moment of inertia, okay? In order to define moment of inertia of a body, we find its kinetic energy of rotation, okay? In order to define moment of inertia of a body, we will find its kinetic energy of rotation, okay? Kinetic energy of rotation. Kinetic energy of rotation. Kinetic energy of rotation, okay? This is omega, and this is your body, okay? And this is point M1, and the distance is R1, okay? And next point is M2, and next is M3, and next is M4, okay? And this is distance is R2, okay? Okay, this is x direction, x, y. Okay, kinetic energy of rotation. Okay, for translatory motion, kinetic energy depends upon mass and velocity v and given by kinetic energy equal to 1 upon 2 mv square. Kinetic energy equal to 1 upon 2 mv square. When a body rotates about an axis, the kinetic energy of its rotation is determined not only by its mass m and angular velocity omega, but also depends upon the position of the axis about which it rotates and the distribution of mass about this axis. Okay, if a body A rotates about an axis xy, with an angular velocity omega, all its particles have the same angular velocity, but as they are at different distances from the axis of rotation, okay, their linear velocities are different. Let the linear velocities of the particle of mass m1, m2, r1, r2 from the axis of rotation v1, v2 respectively. The kinetic energy of the body is therefore equal to the sum of the kinetic energy of the various particles and is given by the kinetic energy of the body, the kinetic energy of the body is therefore equal to the sum of the kinetic energy of the various particles and is given by total kinetic energy equal to 1 upon 2 m1 v1 square plus 1 upon 2 m2 v2 square plus for all particles. Okay, since b equal to r omega, then total kinetic energy equal to 1 upon 2 m1 r1 omega square, plus 1 by 2 m2 r2 square omega square plus 1 by 2 m3 r3 square omega square plus dot. Okay, then this is 1 upon 2 sigma m r square, 1 upon 2 sigma m r square omega square equal to 1 upon 2 omega square sigma m r square equal to 1 upon 2 I omega square, because inertia equal to mr square. Okay, inertia equal to mr square. Then the kinetic energy total equal to 1 upon 2 I omega square, 1 upon 2 I omega square. Okay, where I is the moment of inertia, inertia of the body about the axis xy and is equal to sigma mr square. We have expressed the moment of inertia as mr square. Hence The moment of inertia of a body, the moment of inertia, the moment of inertia of a body, the moment of inertia of a body about an axis is about an axis is defined as the sum of is defined as the sum of defined as the sum of the product of the sum of the product of the mass and the square of the distance, square of the distance of the different particles, distance of the different particles of the body from the axis of rotation of the body of the body from the axis of rotation, from the axis of rotation. In the above case, we have seen that kinetic energy of rotation equal to 1 upon 2 I omega square. If omega is 1, then I equal to 2 into kinetic energy. Okay? So I equal to 2 kE. I equal to 2 kE. Hence, moment of inertia may also be defined. Hence, moment of inertia also can be moment of inertia may also be defined as twice the kinetic energy, twice the kinetic energy of rotation, kinetic energy of rotation of a body, when its angular velocity is unity. Angular velocity is unity. Okay? From the hence, moment of inertia may be also defined as twice the kinetic energy of rotation of a body when its angular velocity is unity. Radius of gyration. Okay? Next, radius of gyration. 1 minute. Radius of gyration. Radius of gyration. Okay? Radius of gyration. Okay? subjugation. If the center of mass of the body is supposed to be concentrated at a point that the kinetic energy of rotation is the same as that of the body itself, then the distance of that point from the axis of rotation is called the radius of gyration of the body about that axis. Okay? If the center of mass of the body, if the center of mass, if the center of mass of the body if the center of mass of the body is supposed to be is supposed to be if the entire mass of the body is supposed if the entire of the mass of the body supposed to be if the entire of the mass of the body is supposed to be concentrated at a point, concentrated at a point, such that the kinetic energy of rotation is the same. Kinetic energy of rotation is the same as that of the body, itself. Then the distance of that point, from the axis of rotation, is called the radius of gyration. Okay. If the entire of mass of the body is supposed to be concentrated at a point such that the kinetic energy of rotation is the same as that point of the body itself, then the distance of that point from the axis of rotation, from the axis of rotation is called the radius of gyration. Okay. Then kinetic energy equal to 1 upon 2 I omega square equal to 1 upon 2 sigma m r square omega square equal to 1 upon 2 capital M k square omega square. Okay. Capital M k square omega square, k square omega square. Okay. And mk square equal to sigma mr square equal to mn in bracket r1 square plus r2 square plus dot upon n, where n is the number of particles of each of mass m into which the given mass m is divided, where n is the number of particles each of mass each of mass m into which the given mass capital M is divided. Okay. Now capital M equal to small m into n, and k equal to r1 square plus r2 square plus upon n whole to the power 1 by 2. Hence the radius of gyration is the square root of hence the radius of gyration is the square root of the mean square distance of the particles, mean square distance of the particles, mean square of the particles, mean square distance of the particles of the body from the axis of rotation, Okay. According to the definition of radius of gyration given above, the distance of k are those of the length L1 alone. Okay. Now moment of inertia I equal to mk square, that is dimensions of inertia is m to the power 1 and l to the power 2. Units of moment of inertia. Units of moment of inertia. Okay. In SI unit, the moment of inertia is expressed as kilogram meter square. Moment of inertia is a scalar. Okay. Moment of inertia is a scalar quantity. Moment of inertia is a scalar quantity because the value of inertia about a given axis remains unchanged by the reversing its direction of rotation about that axis. In other words, it has no direction. The total moment of inertia of a number of bodies about a given axis is equal to the sum of their individual moment of inertia about that axis. So moment of inertia is scalar quantity. Okay. Moment of inertia is scalar quantity. Why moment of inertia is a scalar quantity? What a reason by which moment of inertia is a scalar quantity? We will be known about this thing. Moment of inertia is a scalar quantity because the value of inertia about a given axis remains unchanged by reversing its direction of rotation about that axis. In other words, it has no direction. The total moment of inertia of a number of bodies about a given axis is equal to the sum of their individual moment of inertia about that axis. Okay. Next is heading is the physical significance of moment of inertia. Next. Okay.